Consider a situation like this. Suppose there's a circular region in which there is a uniform magnetic field. Okay, I'm assuming the magnetic field is directed into the plane of the screen. Right. It's a time varying magnetic field. The function, the function could be given to you. Now, if there is a conducting loop placed symmetrically or concentrically in this magnetic field, tell me, will there be current in that conducting loop or not? The magnetic field varies with time. Will there be current in this conducting loop or not?
Yes, sir, there will be a electric field.
There will be induced current. Why will there be induced current? You can see that the magnetic field passing through this conducting loop, it varies from time to time. If field varies from time to time, it means flux varies from time to time. And if there is variable flux through a loop, there will be induced EMF, induced current. Okay. Assume this magnetic field is increasing in strength. Then one of you tell me, in which direction will current be induced in this coil, in this loop? If magnetic field is increasing in strength, what is the direction of induced current? Shashank, what do you say? Will it be clockwise or anti-clockwise?
Clockwise. No, anti-clockwise.
Anti-clockwise is correct. See, the flux into the screen is increasing. Okay. And induced EMF will drive current in such a way that it opposes the change in flux. Inward flux is increasing. So we have to, the induced EMF will have to decrease the flux because it is increasing. And to decrease that, it will produce a field out of the screen. To produce field out of the screen, current will have to flow anti-clockwise like this. Okay. Now see, if current is flowing anti-clockwise like this, it means there is an electric field produced this way. As I said, induced electric field lines form closed loops. So you can imagine an electric field line like this. Okay, it has to be a circle actually, but just for visualization, okay, that the electric field will be in the tangential direction at each point, I'm showing small arrows. Okay, there must have been an electric field produced like this. Now, whether this conducting loop exists or not, the electric field will anyway be produced. Okay, that electric field is the induced electric field. And it is produced because of this time varying magnetic field. Now, let us derive the strength of this electric field. Okay, visualize the current also. Assume this is a ring, conducting ring of radius r. Can one of you tell me how much is the magnetic flux? Let's say magnetic field is B itself. Fine, let's call the magnetic field as B. It is directed into this loop. Okay. How much is the flux passing through this loop? It's a circular loop of radius r. How much is the flux passing through this loop if magnetic field is B? Why are you also silent? Why is it taking so long just to calculate or just to give an answer for flux? What is the formula for magnetic flux?
The integral of magnetic field across def
Where did cross come from? Flux is a scalar quantity. It is integral B dot dA. Anyway, you will do integral B dot dA if field is non-uniform or area vector is difficult to express. Here, the field is non-constant, but it is uniform. Time to time it changes, point to point it does not change. So it's a uniform field. In case of uniform field, you will use the formula B dot A, no integral. The magnetic field, as I said, is B itself. The area is pi r square because it's a circular loop. And the angle between B and A is 0. Magnetic field is perpendicular to your screen. The loop lies in your screen means its area vector is also perpendicular to your screen. So cos 0. Cos 0 is 1. So the magnetic flux passing through this ring is B into pi r square. Okay. If you know flux, then its derivative or the rate of change of flux with respect to time will give you the induced EMF, Faraday's law. Induced EMF is equal to d phi b by dt. I'm not writing the minus sign because I'm only considering the magnitude of induced EMF. So we'll have to take the derivative of magnetic flux B into pi r square. Now r is the radius of the ring which is constant. Okay, radius of the loop. B, the magnetic field, is the one which varies from time to time. So pi r square stays outside the derivative. You will be left with dB by dt. Okay. If you know magnetic field as function of time, you can calculate dB by dt also. dB by dt, right? So we got an expression for induced EMF. EMF is nothing but potential difference. Can one of you tell me how potential difference or voltage is related to electric field? Because our aim now is to derive this electric field. How is potential difference related to electric field? Or how are E and V related?
So the electric field is like negative to potential difference.
Not exactly. Anyone else? Relation between electric field and potential difference. Or how to derive potential difference if you know the electric field. Okay. Delta V is minus integral E dot dr. That is how you get potential difference from electric field. Reverse, if you want electric field from potential difference, it is minus dou V by dou R. Fine. Our aim now is to derive the expression for this electric field. And what we know is the EMF in this loop, in this circular loop, pi r square dB by dt. That we already know. Means we know the total potential difference as you do one round along this loop. Okay. Now, the electric field is in the tangential direction. As you move along this loop, at any position, the dr vector, okay, dr is nothing but the small displacement. At every position, the dr vector will also be in the tangential direction. So the angle between the electric field, induced electric field, and the displacement dr is 0 everywhere as you move along this loop. Then what you can do is, you can write the total potential difference, which is basically the induced EMF. We already know that is minus integral E dot dr is E dr cos theta. Angle between E and dr at every point is 0. So we'll take cos 0. Cos 0 is 1. Okay. And see, we took a circular region in which the magnetic field is present. And the loop was also circular, and those two circles were concentric. There is an intention behind that. If it is concentric, every point of this loop is at the same distance from the center. There is a symmetry in this situation. Okay. And why do we bother about symmetry? If there is symmetry, we can tell for sure that the electric field will be same at all these points on the loop. Okay. For example, you consider one point here. Let's call it X. How much ever electric field is produced at X, the same amount of electric field will be produced here, here, everywhere, because the way the arrangement is the same. The relative arrangement of these points is the same. So they'll all experience the same amount of electric field, or the same amount of electric field will get produced at all points. Now, if the electric field is same at all points, you can put it outside the integral. Then it becomes minus E integral dr only. And if you add all the drs, okay, along this circular loop, what you get is the total length of that circle, 2 pi r. Okay. Let us take the magnitude of EMF. Therefore, the magnitude of the potential difference is the electric field that is induced into 2 pi r. And we know that this is equal to induced EMF. How much was the induced EMF? Pi r square dB by dt. Okay. Pi and r can be cancelled. What will you be left with? E is equal to r by 2 dB by dt. And what we got here is an expression for the induced electric field that is produced by a time varying magnetic field. Fine. And see, the result involves R, which means this result is true only for this system. Okay. There are some assumptions we made here. We took a circular loop for our convenience. Okay. And we took magnetic field also in a circular region. Why that was done is because in this case, you can tell for sure that the electric field, induced electric field produced everywhere on this loop will be the same. At least in magnitude, it will be the same direction. Of course, it will be changing from point to point, but the magnitude of electric field produced at all these points is definitely going to be the same. Okay. So in order to take advantage of that and get some expression for induced electric field, we chose this kind of a geometry. Okay. And observe what we did. Our aim was to derive electric field, induced electric field. And what we know so far in this chapter is to find out induced EMF. Okay. So to get electric field, what we did was we used EMF first. We derived the EMF first, and we used the relation between EMF, which is nothing but potential difference, and electric field. Okay. Now see, you will find this question in almost every book. Okay. In NCERT book, it may not be there, but in standard other like exam preparation books, it will be there. But there is a problem with this derivation. This nobody talks about. This is my personal observation actually. There's a problem with this derivation. See, we talk about potential or potential energy only when it comes to conservative forces. Okay, this is a 11th class concept. Potential energy is associated only to conservative forces. Like spring force is a conservative force. F is equal to minus kx. So we write potential energy stored in a spring is half kx square. Okay. Gravitational force is a conservative force. So gravitational potential energy is minus g m1 m2 divided by r. So like in some cases like earth and particle system, we write it as mgh also. Okay. But see, gravitational force is a conservative force. That's why we talk about gravitational potential energy. Electrostatic force k q1 q2 by r square is a conservative force. Electrostatic potential energy is written as k q1 q2 divided by r. Okay, this you studied in this year itself, 12th class, second chapter, potential and capacitance. So, like potential energies and potentials are associated only with conservative forces. You never talk about potential energy of friction. You never talk about potential energy of air resistance because those are non-conservative forces. Now, what is the problem here? The problem here is that induced electric field forms closed loops. Understand this carefully, all of you. Suppose this is an induced electric field line. Okay. When do we say a force is conservative? We say a force is conservative when the work done by that force in a closed path is zero. Okay, that is the definition of a conservative force. Work done by a particular force in a closed path should always be 0, then the force is considered conservative. Now see, in this, uh, along this electric field line, if you take a charge, assume it's a positive charge only. Positive charge experiences force in the direction of field. So here the force will be this way. When the charge comes here, the force will be this way. When the charge comes here, the force will be this way. Positive charge, it experiences force in the same direction as the electric field. Okay. Imagine moving this charge along this circle. If you are moving the charge along this circle, the displacement is also in the same direction, ds. At every point, displacement will be this way. Okay. Now, if you see at all points, force vector, force exerted by this electric field, and the displacement vector ds, they are in the same direction. Then the work done in this closed path will be integral f dot ds. That's the general formula for work done. And because force and displacement are in the same direction everywhere, the dot product is going to be positive everywhere. And if you integrate positive terms, the answer will also be positive. Okay. That means you get work done in a closed path as a positive value, not 0. Therefore, you can say that induced electric field, E bar induced means induced electric field, is a non-conservative field. Because had it been conservative, work done in a closed path would have become 0. Here it is definitely non-zero. Okay, so it's a non-conservative field. And for non-conservative fields, non-conservative forces, you should not talk about potentials and potential energies. So what I'm saying is, you should actually not use this relation. You should not use this equation to relate induced EMF and induced electric field. EMF is potential difference, okay, but you can't use this formula to relate it to the electric field. Okay, so there is something wrong in this derivation, but many books tend to do this. Even in exams, they have asked questions based on this, but this is my personal observation that you should, like, potential energy, potential difference is not associated with non-conservative force. You should not talk about it at all. So when this electric field here is non-conservative, how are they using this to find out the potential difference? It is meaningless, should not be done, but they do it. Okay, that's why in NCERT textbook they don't. I don't think there is any relation between. I mean, relation given for induced electric field, but other textbooks they tend to do this. Anyway, remember the procedure and see the result that we derived for induced electric field. Of course, forget about whether the procedure is legal or not. We got some answer for it. This is valid only for this particular case. Okay, a circular region in which there is a uniform magnetic field, and we considered, like, our aim was to derive induced electric field. We considered a concentric circular loop and we got the expression for it. And what expression did we get? We got that electric field depends on r. R is the distance from the center of that circular region. Just a moment, let me copy this. So as I said, whether there is that conducting loop or not, the electric field will anyway get produced. Okay, so let's say it got produced. If the loop is there, current will also flow because conducting loop will have electrons in it. They will be driven by this electric field. If loop is not there, the electric field will only be there. Okay, so what was R in this derivation? See, the magnetic field was in a circular region, right? R is the distance in that circular region from the center where you want to find out the electric field. This distance was R. So only for this kind of a magnetic field, you can tell how much induced electric field it produces. R by 2 dB by dt. So as you go away from the center, as R increases, the electric field strength increases. Okay. So is the derivation clear to all of you? Any doubts in this? How we derived the expression for induced electric field in one particular case. We made use of induced EMF and the relation between EMF, which is potential difference, and electric field. Okay. See, not just this one, all the derivations that we are discussing, do them once on your own. Okay. You should know what the aim of a derivation is and what the assumptions in that derivation are. Okay. Because mains, NEET and all, it's okay. But in JEE advanced, you will definitely come across new situations. Okay. Where the formula that you derive may not be applicable, because every formula that you derive in your syllabus will be specific to particular situations. Okay. There's no one formula which always works. Every formula has conditions. Okay. Like take the simple range formula for projectile, ground to ground projectile, u square sine 2 theta by g. It's valid only when there is no air resistance. It's valid only when there is no horizontal acceleration. Okay. By some means, if they include horizontal acceleration, what to do? If you want to, or if you want to get yourself to that level where you will be able to answer questions when the situation is changed also, you should know the derivation, how we are deriving particular result. In advanced, they'll make some small changes in the situation and check whether you can apply your knowledge of physics in that new situation or not. So that knowledge of physics will be there in derivations, not the final formula. So not just this case, as I said, keep practicing derivations now and then. In fact, when I used to prepare for JEE Advanced, like they used to conduct, I studied in Chaitanya, they used to conduct exams very frequently, like once in 3 days or so, they used to conduct a 3-hour exam, 3 hour, 6-hour exams also sometimes. Now see, for the level of preparation that I used to do, whatever questions I could answer in 1.5 to 2 hours. The other questions seemed like not possible for me to do. So what I used to do in those exams and all, or whenever I get bored while studying also, what I used to do, like think of some concept, anything. Okay, like some of you may be interested in optics, some of you may be interested in thermodynamics, whatever it is. Think of any chapter that you like, derive all the theory of that chapter on your own. Okay, if you have mastery on that derivations, how every formula is derived, what are the concepts involved, what are the assumptions involved, then you can solve questions easily. Then you can attempt new questions also easily with confidence. Okay, so whenever you have time, no, revise derivations. Okay, so what all have we discussed in this chapter so far? First is Faraday's law, how to find out how much EMF will be induced, d phi by dt. You need to get an expression for flux and differentiate it. Okay. Then Lenz's law tells you in which direction the induced EMF will try to drive the current. Okay. It will always try to oppose the change in magnetic flux. So if flux in a particular direction is increasing, the induced EMF will produce a field in the opposite direction. If flux in a particular direction is decreasing, induced EMF will produce a field in the same direction to support that field. Okay. Then we solved some problems. Then we talked about why there will be an EMF induced when flux changes. Now for changing flux, there are many ways. You can change area of the loop or the orientation. In that case, conductor will move in a magnetic field. Motional EMF comes into play. Another way to change flux is by changing the magnetic field itself. In this case, induced electric field gets produced, and that's what we have been discussing in the last class and this one. Okay. Fine. Next thing is magnetic induction. Basically, from here onwards, we'll be discussing how these concepts are applied in like making a few machines, you can say. Okay, like there's something called an inductor, there's something called a generator. Okay. How these things work, we can understand if we know about induction. See, the basic idea is that when flux through a loop or a coil changes, it induces EMF in that coil, we can drive current. Okay. So basically, electromagnetic induction is all about sending electrical energy wirelessly. Okay, now you all must have heard of wireless charging. Have you all seen wireless charges or not?
Yeah.
At least
Yes, sir.
on screen you must have seen. Yeah, Personally, I also have never used a wireless charger, but basically there is a charging pad. You put the compatible device on it, it gets charged. You don't have to plug in the USB or anything. Can any of you tell me how it works?
Sir, there's a magnet attached to the back of the phone, and there's a magnet to the base of the charger. And when both of them are in contact, it gets charged.
See, magnet being in contact with magnet cannot simply charge a device. Any other answer? How does wireless charging work?
When the phone is placed on the MagSafe pad,
Huh.
something gets induced in the phone, the current.
Okay. See, basically, to charge the battery of a phone, you have to somehow produce current. Okay. In fact, to charge a battery, you need to drive current through that battery in the opposite direction. Usually, what happens? Current flows out of the positive terminal of a battery. In that case, it loses its energy. If current is forced to flow into the positive terminal of a battery, then the battery gets charged. If it's a rechargeable kind of battery. Okay. So we have to somehow produce current in that battery of the mobile phone. Normal chargers, what they do, you connect it to the power socket, they will produce current. These wireless chargers, what they do is they produce current in the battery or in the phone circuit. They produce current through electromagnetic induction. Okay. So it's a simple system. See, we call it wireless charging, but there is a wire involved, right? There is power supply involved. The charging pad has to be connected to a power supply. Whether you have seen it in cars, if it's the wireless charging pad in a car, it will be connected to the battery of the car. If it's a wireless charging pad that you are using at home, it will be connected to the power socket. Okay, there may be wireless these things also, like portable chargers. That portable charger also has a battery which you have to charge at some point. Okay, so even though the charging is wireless, there is some power supply involved. Okay, so basically how it works is this. Consider one coil like this, having a number of windings. And another coil. Okay, let's say there are two coils. They are coaxial, means they have the same axis. Right. Now, the lower coil, you can call it as the primary. Assume this coil is inside the charging pad. Okay, and the other coil is in the mobile phone. You can call it as the secondary. Fine. The coil that is inside the charging pad, it has to be connected to the power supply. The charging pad should be supplied power. Okay. Usually we provide something called an alternating current. You'll learn in detail about alternating current in the next chapter. Basically, it's a variable current. Okay. For some time it flows in the forward direction. For some time it flows backward. So forward, backward movement of electrons will be there. It's a variable current. Now when current flows in a coil, you know it produces a magnetic field. Okay. Assume for a moment that current is flowing this way. If current flows this way, curl your right hand fingers, magnetic field will be produced in the upward direction. And that magnetic field passes through the other coil. The magnetic field produced by this first coil passes through the second coil. Okay. And see, the current in the first coil, primary, is a variable current. Then this magnetic field also will be a variable magnetic field. Now what is happening in the secondary coil? A variable magnetic field is passing through it. Then it produces a variable flux. A flux that varies with time, which will generate EMF, and charge the battery of the mobile phone. Okay, so to get an idea of how much flux can produce how much current in a particular coil, okay, we learn about something called induction of that coil. Okay. In induction, there are two types. One is self-induction. Now, you consider a circular loop like this, circular conducting loop. It is not under the influence of any magnetic field. There is no external magnetic field. There is this loop. Suppose the loop has its own current. Assume the current is clockwise. Tell me, will it produce a magnetic field or not? If yes, in which direction is the magnetic field produced by its own current?
Downwards.
Into the screen. Okay, curl your right hand fingers along the flow of current. You get a magnetic field into the screen. Who is producing this magnetic field? Is it an external agent or the loop's own current?
The loop's name.
This is the magnetic field due to the loop's own current, right? And if there is a field passing through the loop, it means there is a flux passing through this loop. So the own current of a loop or a coil can give rise to a flux in that coil. Okay. Therefore, current flowing in a coil can produce magnetic flux in that coil. Okay. The ratio of current in a coil to the magnetic flux produced in that coil is what we call as self-induction. Okay, self-induction denoted by the symbol L. We write phi is equal to Li, or you can say L is equal to, L is nothing but the self-induction, is equal to the magnetic field produced in the coil divided by the current in that coil. It's a scalar quantity. Sorry, I said magnetic field. That's a mistake. Magnetic flux produced in the coil divided by the current flowing in that coil. This is a basic definition for self-induction of a coil. The ratio of magnetic flux to the current of the coil itself. This flux is not flux produced by an external agent. The current is also not current flowing in some other coil. The loop's own current producing flux through that loop itself. That ratio is what we call as self-induction. Okay. What is the SI unit of magnetic flux?
Weber.
Weber. Okay. Tesla meter square, magnetic field into area, which is called as Weber. SI unit of current is ampere. And Weber per ampere is called Henry, denoted by capital H. That's the SI unit of induction. Okay. So L is equal to phi divided by I. You can write the magnetic flux through a coil is its self-induction multiplied with the current in that coil. Phi is equal to Li. We'll be using it this way. Okay, when we actually make use of magnetic induction, okay, we'll be using it this way. So remember, self-induction of a coil relates the current in the coil to the magnetic flux that it produces. Okay, and why is this important? Suppose by some means you are able to vary that current. Okay, if current is variable, then the magnetic flux through the coil also varies. Obviously, the field produced by it will change, then the flux produced by it will change. There will be an EMF induced in that coil. So simply by changing current in a coil, you can induce EMF. Okay, and to do those calculations, you'll need to know how much is the self-induction of that coil. Okay, derive the dimensional formula of self-inductance, all of you. Make it fast. Okay, I got one answer as m I power minus 2 L square T power minus 2. Fine. Can you tell how you derived?
So I divided the diameter formula of flux with current.
You remember the dimensional formula of magnetic flux?
No.
Okay, anyway, see, you just have to think of some way to get the answer quickly. Okay. Magnetic flux is field into area. So magnetic field area divided by current. Current's dimension is easy only. Area is also easy. Then magnetic field, if you remember the dimensional formula of magnetic field, fine. Otherwise, I prefer to use F is equal to QVB. Then B becomes F divided by QV. So in place of magnetic field, you can write force divided by charge and speed. Okay, that way you can get the dimensions of self-inductance. Fine. So L here is called the self-inductance of a coil. Right. Now see, inductance in magnetism is similar to capacitance in electrostatics. Can one of you tell me what a capacitor is used for? What are capacitors used for?
It stores charge.
Not charge. The actual intention is to store energy, okay, which can be quickly retrieved. It stores electrical energy, you should say. Stop saying capacitor stores charge. Okay. And the definition for capacitance, okay, Q equal to CV, C is equal to Q divided by delta V. If you put charge on a capacitor, like if you charge the plates equal and opposite to the magnitude Q, a potential difference develops across it. Okay. The ratio of charge to potential difference is what we call capacitance. Now, inductance in magnetism is somewhat similar to capacitance in electrostatics. If current passes through a conducting coil, okay, a flux gets produced in that coil. Okay. It's like when you charge a capacitor, a potential difference gets produced. When current passes through a coil, magnetic flux gets produced. So ratio of flux to current is what you are calling inductance, self-inductance. Somewhat similar to ratio of charge to potential difference, capacitance. Capacitor stores electrical energy, inductor stores magnetic energy. There's a device called an inductor. Okay, that's what we are going to discuss now. Basically, any coil can be called an inductor. Any system which can produce magnetic flux through itself when current passes through itself can be called as an inductor. Okay, so you just wind a coil in the form of a spring, wind a wire in the form of a spring, it's an inductor. Okay, even a single loop is an inductor. So any system which can produce a magnetic flux through itself when current flows in it is called an inductor. Okay, let us derive an expression for self-inductance in one case. Self-inductance of a long solenoid. Consider a long solenoid. Assume it has smaller number of turns per unit length. The total number of turns in a long solenoid, nobody will talk about it. Okay, because it will have a lot of turns anyway. So number of turns per unit length is what you will usually be given. Let it be small n. Can one of you tell me the expression for magnetic field produced inside a long solenoid?
Mu naught small n I.
Mu naught ni, correct. Okay. Is it uniform, not non-uniform?
Uniform.
In a long solenoid, you get a uniform magnetic field. If the magnetic field is uniform, it's easy to write an expression for the flux. That's why we consider this case. Assume this is the long solenoid. Small n number of turns per unit length. Assume its radius is r. Okay, why we care about the radius is because we need to write an expression for the magnetic flux when current passes through it. Okay, so assume the radius of the solenoid is r. Now, what we want is self-inductance of the solenoid. So what we will do, not just in this case, in any case, if you want to derive inductance, assume some current flows through it. Okay, so assume current in the solenoid is I. When current passes, it produces a magnetic field. So we'll start with an assumption for the current. Based on current, we will derive magnetic field and magnetic flux through the coil. Then self-inductance by definition is magnetic flux divided by the current. Now the flux will depend on current anyway. When you divide it by current, it gets cancelled. So your assumption doesn't really matter finally. So you start with an assumption, it will get cancelled at the end. You'll get an answer for inductance. Try this, all of you. Assume a current I flows in this solenoid. First step. Because finally what we want is flux by current. Flux depends on magnetic field. So write the expression for field produced by it. Then find out flux through each turn of the solenoid. Okay, let's say total length is L. That length is also important. Find out flux through each turn of the solenoid. Then find out the total flux through the solenoid. Then inductance. Flux divided by current should give you the inductance. Do this quickly. I got one answer as n square mu naught a L. Okay. Anyway, the radius of the solenoid is given to you, so you can express area in terms of that. Isha, can you unmute yourself? We'll discuss quickly.
Yes, sir.
How much is the magnetic field in the solenoid?
Mu naught Ni.
Okay. Listen, all of you. Mu naught Ni is the magnetic field produced by the current only. Okay. And here, of course, there is only that current. Who else is producing magnetic field? We'll consider only that. But why I'm telling you this is because the solenoid could be filled by some other material sometimes. Okay, we'll come to that in detail. We'll discuss that in detail. If it is filled by some other material, in the last chapter, magnetism and matter, we discussed. If a material is placed in an external magnetic field, that material gets magnetized. and it produces an additional magnetic field. Okay. Now the current flowing in the coil produces the magnetic field mu naught Ni. To that material, this is the external magnetic field. Not to the solenoid. This is the solenoid's own magnetic field only. But to the material inside the solenoid, this is an external field. Okay. And that material, if it gets magnetized, it will produce an additional magnetic field. Then the net magnetic field has to be considered. Okay, we'll discuss that. Okay, for now, let us assume there is no other material present. It's an empty solenoid. In an empty solenoid, this itself will be the magnetic field produced, mu naught Ni. Okay, so Ishat, can you tell me the direction of this magnetic field? Anyone? What is the direction of this?
Left.
Okay, see, left or right depends on how the current is flowing. You should say it is parallel to the axis of the solenoid. Okay, if current flows like this, then curl your right hand fingers this way, the magnetic field will be to the left. But if current flows the other way, say downwards, then it will be produced to the right. So it can be produced either way, depending on how the current flows. But it will be parallel to the axis of the solenoid. Why we are bothered about direction of magnetic field is because we need to calculate the flux now. Flux is B dot A. Now the magnetic field here is uniform. It's a long solenoid, uniform magnetic field. Only at the edges it will be slightly less, but anywhere comfortably inside the solenoid, the magnetic field is mu naught Ni. Okay, now field is along the axis. If you take any one loop or coil of this solenoid, let's consider this one. I'm highlighting it in blue. Consider one coil of the solenoid like this. Actually, these are tightly wound coils. You won't be able to notice this gap. Okay, the gap will be very less. Then each turn, can any of you tell me in what shape each turn will be if that gap is very less? Each turn of the solenoid will be in what shape?
Helical.
No, if that gap, like if the threading is too close, what shape will each turn be?
Circular.
Someone said something, it was not clear.
Circular.
Circle, it will be a circle. Okay, correct. It's just like a ring. Each turn is like a ring, just a slightly separated ring, you can say. Okay, at one point, it's slightly separated. Fine. So you can imagine the area of cross section. The area of cross section will be a circle's area pi r square. And if you imagine it as a circle, its area vector is going to be in this direction, either to the right or to the left. It's going to be along the axis, because you have to consider it like this. This is the circular loop. There are a number of circular loops in that solenoid. And we know area vector of a loop is perpendicular to the loop. Okay, so it's either this way or the other way, but it's parallel to the axis. Okay, magnetic field is parallel to the axis. The area vector of each turn is also parallel to the axis. That means the angle between magnetic field and area vector is 0. Then the flux through each turn, it's a uniform magnetic field. Now we can use the formula B dot A, which is BA cos theta. B is mu naught Ni. Area is pi r square. Cos theta is cos 0, which is 1. Okay. So this is the flux through one turn of that solenoid. When flux varies, in that one turn, there will be an EMF produced. So each turn of the solenoid will behave like a small battery. And there are a number of batteries like this connected one after another. They are all in series. So all the EMFs will get added. And if you want the total EMF induced between this point and this point, you have to consider the total flux induced. Okay, so you'll have to add the flux of all the turns to get the total flux in the solenoid. Isha, can you tell me how to express the total flux through this solenoid? We got the flux in one turn. How to express the flux in all the turns combined?
So we add them
How many times? Or how many
N.
turns are there?
N times.
What is n here?
The number of turns.
No, n is not the number of turns. Read there. Number of turns per unit length. Okay.
Okay.
So if you want total number of turns, how will you get that? Anyone? Small n is actually total number of turns divided by the total length. So if you want total number of turns, capital N will be small n multiplied with L. Okay. So total flux will be flux through each turn multiplied with the number of turns. Okay. Flux through each turn we got. Yeah, Pradyum, the answer you sent is correct only. Flux through each turn is mu naught Ni pi r square. Number of turns is NL, small n into L. That's the total flux in this solenoid. So we can write this as mu naught N square L pi r square into I. And as I said, the flux will depend on the current. Okay, that's what we are getting here. Flux depends on current. Okay, but anyway, this is not the final thing that we wanted. We wanted to derive the self-inductance of the solenoid, long solenoid. And we know by definition, self-inductance is total flux divided by the current. So if you divide this flux by current, I gets cancelled. And what will you be left with? You'll be left with mu naught N square L pi r square. This is the formula for self-inductance of a solenoid. The ratio of flux produced in the solenoid to the own current of the solenoid. Does flux, okay, flux depends on current and all, that's fine. But the final inductance that we derived, look at the result and tell me, all of you, does it depend on current?
No, sir.
It does not. Okay. Inductance is the ratio of magnetic flux to current. So by looking at that formula, you may feel that it depends on current. But no, flux depends on current. And when you divide that by current, the answer will become independent of current. So irrespective of how much current flows through the solenoid will have this much inductance. Okay. And when I said this is similar to capacitance, this is also one of the reasons. Can one of you tell me the factors on which capacitance of a capacitor depends? Capacitance, the basic formula is Q divided by delta V. Okay. But when you give more charge, you get more potential difference. Those two are proportional to each other. It's like in inductance, when current increases, flux increases proportionately. Their ratio is inductance and it is independent of current. Capacitance also, when charge on the plates of the capacitor increases, the potential difference between them increases, but the ratio will be fixed. Can one of you tell me on what factors this ratio depends? Capacitance depends.
It depends on the geometry and construction of the capacitor.
Geometry construction is the same. It depends on geometry, that is the shape of the plates of the capacitor, the gap between them and all. It depends on how the capacitor is built. And it also depends on the medium between the plates of the capacitor. Okay. And medium between the plates of the capacitor. For example, the capacitance of a parallel plate capacitor is epsilon naught A divided by D. Epsilon naught is permittivity of free space, vacuum. If it is filled with a dielectric, no, completely filled with a dielectric, it becomes epsilon of that medium into A divided by D. Or you can write it as dielectric constant into epsilon naught into A divided by D. When the parallel plate capacitor is completely filled with a dielectric. We know this. Okay. So look at the factors on which it depends. Medium And area and distance between the plates are geometrical factors. So it depends on the medium and the geometry. Now you look at what the inductance of a solenoid depends on. Can one of you tell me what mu naught is? What is mu naught?
Permittivity.
Permeability of free space.
Permeability.
Okay, so this is a factor which depends on the medium. If the solenoid is empty, then this is its inductance. If the solenoid is filled with some other material, you'll have to use permeability mu of that material. Okay, this is what I was telling you in the last last chapter, magnetism and matter. One of you had asked me, is this chapter important? In magnetism and matter, we talked about something called susceptibility and permeability of a material. So we'll be using those ideas here. If a solenoid is filled with some other material, what to do? How to find out inductance? How much flux will be produced? That you can do if you know permeability of that medium. Okay, and permeability of a medium depends on its susceptibility. Okay. Anyway, we'll combine all those and solve questions. So this is a factor which depends on medium. What is N? N is number of turns per unit length. Okay, so it depends on how tightly the coil is wound. That is a geometrical factor. L is the total length of the solenoid, geometrical factor. R is the radius, geometrical factor. So these terms are geometrical factors. So self-inductance of a coil also, like capacitance, depends on the medium inside that coil and the geometry of the coil, the shape of the coil. Okay, we proved it in case of a solenoid, long solenoid, but it is true for other coils also. In other coils, we can't derive self-inductance because we don't know that much mathematics. Okay, for example, we know a circular loop produces a magnetic field. A single circle carrying current produces a magnetic field. But we know the expression only for magnetic field at its center. At other points of that circle, we don't know the expression for magnetic field. So, and if you don't know the expression for magnetic field at other points, you can't write an expression for flux. And you can't divide flux by current and get self-inductance. Okay, so mathematical limitations are there, but every coil has its self-inductance, not just a solenoid. A single turn can also have inductance. Okay. Let's solve some questions based on this. Ratio-based questions are very common. Let's try that itself. A solenoid having small n turns per unit length and of radius small r is stretched. Let's say it is stretched to twice its length without changing the radius or without varying its radius. Okay, you have to derive the ratio of inductance, new inductance to the old inductance of the solenoid. Means after stretching to before stretching, what is the ratio? If you are stretching, you are changing the geometry. So you can expect a change in the inductance. So that ratio is what you need. Try this, all of you. Okay, I got only one answer so far. 2:1. We'll see. See, we are stretching the solenoid. I can use this diagram maybe. Visualize the situation carefully and then it's done. So let's say this is the initial solenoid, original solenoid. Without changing its radius, it is being stretched. So I can literally do this. Okay, this is what happens. Radius stays the same. It is stretched to twice its length without varying the radius. Okay. Rishi, you gave answer as 2:1. How did you solve?
Sir, I just put in the formula and then I put the length as 2L, and then after I cancelled everything it out, it comes out as 2:1.
Okay. So you are using this mu naught n square L pi r square nu to mu naught n square L pi r square old value. And you took everything to be the same except for length.
Yes, sir,
Final
because the
length.
new length is twice, right? It's stretched.
So you are saying it is 2:1. Okay. There is a mistake in this. Pradyun, can you identify the mistake? Or Rishi, you also think about it. There is a mistake in this. And it's a very common mistake. Students always overlook that point. Can any of you tell me what is wrong in this? Okay. What students forget? No, Pradyun, it's not about R. It's clearly mentioned in the question that it's being stretched without varying its radius. Okay.
Sir, is it the fact that it won't be in a specific circular shape because it's stretched out and the loops are a bit
No,
further?
no. The circle won't be disturbed that much. See, these diagrams that I have shown here, these are exaggerated actually. Original solenoid also won't have this much gap. Okay. The gap will be very, very small. Even when you stretch it to twice its length, the gap will still be quite small. Okay. So it's not, that is not the problem. What students tend to forget is that small n is not the number of turns, it's the number of turns per unit length. Small n depends on length. So if length is changed, small n changes. Okay, you have to keep that in mind. When you stretch the solenoid, now what happens? The total number of turns remains the same. But if original length is L and final length is 2L, then original small n value will be total number of total number of turns by total length, n by L. The new value of small n will be n divided by 2L. Okay. So new value of small n is original value divided by 2. Small n gets halved. Okay. Students always overlook this, but it's a very common mistake. Remember, small n is number of turns per unit length. Okay. So when length changes, small n value also will change. Now, if you get back to this problem, length became twice, that's fine. But the new value of small n is half the original value of small n. So small n initial and small n final. Okay, new to old we are taking, no? So small n new to small n old, that ratio will be 1 by 2. And when you square it, it will become 1 by 4. So 1:4. The answer is 2:4. Basically, 1:2 is the answer. Okay, like the final answer will be 1:2, not 2:1. New length is twice the original length that we have considered. Okay. So L like new length by old length, the ratio 2:1 we will get. But new number of turns per unit length to old number of turns per unit length, that ratio also should be taken. Okay, and that ratio will be 1 by 4. So 1 by 4 into 2, answer is 1 by 2. Okay. Next, solenoid completely filled with a medium. Just a moment. So understand what happens here. Self-inductance is the magnetic flux, ratio of magnetic flux to the current. And magnetic flux depends on how strong the field is. Now imagine a current flowing up like this. If a current flows up like this, curl your right hand fingers along the flow of current, you get a magnetic field directed to the left. There'll be a magnetic field produced to the left. So this side behaves like North Pole, this side behaves like South Pole. You call this an electromagnet. Okay. If there is some other medium placed inside this solenoid, let's say the medium completely fills the space inside the solenoid. Just a moment, let me adjust this. Okay, assume it is also in cylindrical shape so that it exactly fits the solenoid. Okay. So that yellow material that we have considered is now in the presence of the magnetic field produced by the solenoid. Solenoid produces its own magnetic field mu naught Ni. In vacuum, that's the field it produces. That field produced by the current in the solenoid is an external field to this material. Now the material will produce its own magnetic field. Okay. That magnetic field can add up to the original magnet. Now it depends on the material. I'm not saying all materials will produce magnetic field in the same direction as the original one. We had discussed this in the last chapter. Okay. Paramagnetic and ferromagnetic, they produce an internal magnetic field in the same direction as external magnetic field. So they'll make the field stronger. But diamagnetic, we know internal field will be opposite to external field. They'll make the field weaker. Okay. So depending on the type of material with which you fill the solenoid, you may get additional field in the same direction as mu naught Ni. You may get additional field opposite to mu naught Ni also, but the field will get disturbed somehow. Net field will be disturbed. And if net field will be disturbed, net flux will be disturbed. Okay. That is how self-inductance depends on the medium. If flux is disturbed, inductance is disturbed. Okay. That's why it depends on the medium. And how to include the medium factor in this result? Just wherever you use mu naught. Okay. See, if it was vacuum, the field produced would have been mu naught Ni. If it's a solenoid, if it is, let's say, a circle at its center, mu naught I by 2R. Mu naught, you'll see those terms if it is vacuum. Instead of vacuum, if you have the space filled with some other medium, mu naught is to be replaced by mu of that medium. That's all. That's the only thing you need to take care of. So we saw that the self-inductance of a solenoid is mu naught N square L pi R square. So if it is filled with some other material, then it becomes mu N square L pi R square, where mu is the permeability of that medium. That's all. And there are other ways to write it. Permeability of a medium divided by that of vacuum is what you call as relative permeability. And relative permeability in magnetism is 1 plus X, where X is susceptibility. All this we had discussed in the last chapter. So in place of mu, you can also write mu R into mu naught. You can also write 1 plus susceptibility into mu naught. In any of these ways you can express. So solenoid becomes mu R mu naught n square L pi R square, self-inductance of a solenoid. You can also write that as 1 plus X, where X is susceptibility of the medium, into mu naught n square L pi R square. And this way it will be better. See, for diamagnetic, susceptibility is negative. X is a value between -1 and 0 for diamagnetic. If you do that, this number becomes less than 1 for diamagnetic. And if this factor is less than 1, that means the inductance of the filled solenoid is less than inductance of the original solenoid. So if you fill a solenoid with a diamagnetic material, its inductance decreases. Why? Diamagnetic material produces an opposing magnetic field and it reduces the overall magnetic field. And if overall magnetic field is reduced, the flux gets reduced, the inductance gets reduced. Okay. But suppose the material is paramagnetic or ferromagnetic. Para and ferro, you have positive susceptibilities. And if susceptibility is positive, this factor becomes greater than 1. 1 plus a positive value, it becomes greater than 1. In that case, the inductance of the filled solenoid will be more than the inductance of the empty solenoid. Okay, so by putting a material inside the solenoid, you can increase the inductance, you can decrease the inductance. And this is the actual reason why inductance depends on the material with which the coil is filled. Okay, any doubt in this, all of you? Hope you understood why inductance depends on material. Of course, it depends on geometry because flux is field into area. Area depends on geometry. Okay. The field produced also depends on geometry. Okay. Fine. Let's see if you all can solve this. Solenoid. Let's say all those values are given to you. Length is known. Number of turns per unit length is known. Radius is known. So the geometrical factors are considered. They are known to us. Assume half the solenoid is filled with one material and the other half is filled with, or okay, let's keep the other half empty. So instead of completely being filled with a material, it is partly filled. Half filled, exactly half filled. The question is to derive its self-inductance. Think of how to do it. And materials susceptibility is given to you. Let's take susceptibility as X itself. So I want the answer in terms of X. Tell me your ideas first. How do you think its inductance can be derived? See, we know the inductance of an empty solenoid. It is mu naught n square L pi R square. Why we can't simply replace mu naught with mu in this case is because the solenoid is not completely filled with the material. So we are not able to do that. Then how else can we derive the inductance when it is partially filled? When formula cannot be used in a particular situation, you have to fall back on the basics. Okay. Can one of you quickly tell me how we got this in the first place? Quickly tell me the steps involved in deriving the inductance of an empty solenoid.
So we first found the magnetic field, then we found the flux of each turn, then we combined that,
Yes.
and yeah, that's all.
So we assumed some current. We got the field, we got the flux through each turn, then we got the flux through the entire solenoid, and we divided them from the definition of inductance. L is equal to phi divided by I. You have to do that here. See, as I've told you this before also. When a formula cannot be applied in a situation, you have to think of the way the formula was derived. Okay, that's why in today's class also I told you derivations are very important. Okay, assume current I. First tell me, how much is the magnetic field produced by the current? Not the material inside, only the current. How much field does it produce? It's a solenoid. Current produces a field of mu naught Ni. Okay. How much field does the material produce now? Listen, all of you. This is where the ideas from last chapter come into play. For the material, this is an external magnetic field. For the material. And I'm asking you, what is the internal magnetic field of the material? External magnetic field and internal magnetic field are related by susceptibility. B internal is X times of B external. That is what is susceptibility. I is equal to X times of H. I is nothing but internal field divided by mu naught. H is external field divided by mu naught. Mu naught gets cancelled. Internal field is X times of external field. Therefore, the magnetic field produced inside the material will be X into mu naught Ni. Okay. Now there are some turns of this solenoid where there is current and also material. There are some turns where only current is present, material is not present. Okay. Let us divide the solenoid into two regions. Call this region A and call this region B. In region A, our aim is to get the flux somehow. Okay. For flux, you need to consider both magnetic fields. The current will produce some flux. The material also will produce some flux. You have to include both of them. Okay. Net magnetic field, you'll have to add these two, is 1 plus X times of mu naught Ni. Mu naught Ni is due to current, X mu naught Ni is due to material. Add both, you'll get the total magnetic field in that region. So the net magnetic field in region A is 1 plus X times of mu naught Ni. Whereas in region B material is not there, no? So the net magnetic field will simply be mu naught Ni. Okay. Actually, there is a catch in this also. The material, we know it produces a magnetic field. Okay. Those field lines, the field lines of that material pass through this region also. Okay. We are ignoring that. The rest of the solenoid does not only have mu naught Ni, it will have some magnetic field from the material as well. Okay. We are ignoring that. If you ignore that, then it will only be mu naught Ni. Okay. So we know the net field in region A, net field in region B. If you know field, multiply with area, you'll get flux. Therefore, flux in the region A, field is 1 plus X times mu naught Ni. Area of each turn is pi r square. Number of turns in region A is total number of turns divided by 2, because exactly half the solenoid was filled with that material. So this is the total flux in the region A. Total flux in region B will simply be mu naught Ni pi r square NL by 2. Add these two, you'll get total flux through the solenoid. 1 plus x by 2 and 1 by 2. Okay, the rest of the terms are same in both cases. 1 plus x divided by 2 is there, and here there is a 1 by 2. If we didn't write anything, means there is a 1. Okay, 1 plus x by 2 plus 1 by 2 can be written as 2 plus x by 2 whole divided by 2. So the total flux in the solenoid becomes 2 plus x whole divided by 2 into mu naught n square L pi r square I. Therefore, the inductance of this solenoid becomes 2 plus x divided by 2 mu naught n square L pi r square. That's the total inductance of this partially filled solenoid. But yeah, remember there is a small thing that we neglected in between. We neglected the magnetic field produced by this material in this region. Materials can produce magnetic field outside also. Okay, once they get magnetized, once dipoles develop inside, those dipoles will develop a field outside also. Okay. We are ignoring that. Actually, in exams, they may not ask you questions like this, but they can ask you questions where half solenoid is filled with one material completely. The other half is filled with another material completely. This can be asked because in this case, throughout the solenoid, you are considering fields of both of them. Current field is considered, material field also will be considered throughout the solenoid. Then they can ask you questions like this. Okay, and you'll find questions like this in your worksheet. But remember the idea, the direct formula is not applicable in this case because the entire material, the entire solenoid is not filled with that material. So we solved it from the basics. We assumed a current I to be passing. Then we saw how much field is produced at different places in the solenoid. Based on field, we got flux, total flux by current gave us the inductance. Okay, so today, what all we discussed? First, we discussed one case where we can derive the expression for induced electric field. Okay, so a circular region having a magnetic field, and at a certain distance from the center of that circle, you can tell what is the induced electric field. The idea we made use of, we know how much EMF is induced. EMF is nothing but potential difference. From potential difference, we are getting the electric field. But as I said, in this derivation, there is a small catch. For induced electric field, you can't define a potential energy or a potential at all because induced electric fields are non-conservative fields. They form closed loops, so they become non-conservative fields. So that is there, but most books, they don't consider that. Don't know why. Next, we started talking about induction. And induction, we first discussed self-inductance of a coil. Self-inductance is the ratio of flux produced in the coil to the own current of the coil. L is equal to phi divided by I, phi is equal to Li. Dimensions, units we discussed. Then for a long solenoid, we derived and one problem based on that. And when medium changes, what to do, how to consider the presence of a medium to find out the inductance of a coil. Okay. Fine, then we'll continue in next class on Tuesday. We'll discuss a little more about self-inductance, we'll solve more problems. Then we'll move on to something called mutual inductance. Current in one coil producing flux in another coil. That's the idea we use in that wireless charging. Okay. So how much current in one coil can produce how much flux in the other coil, how much EMF in the other coil, all that we will discuss. But in self-inductance also, there is something more to be said. How much energy an inductor can store, how much potential difference will be developed across an inductor, how to use it in circuits. Yeah, a lot needs to be discussed. We'll do all that. Okay. Yeah, if you have any doubts, you can ask.
No, sir, that's it. Thank you.
Okay.